All right, thank you. So hi everyone. Today is going to be simply a review of all the material that we've covered before. So we ran the survey yesterday, and there was, about, 6 topics that, people can choose from. And it looked like data extraction and analysis was big on, people were kind of confused about that. And also, fitting models and building models, linear or nonlinear. People were also confused about that. And also a little bit about, kind of importing data and everything. So I'm going to be touching on primarily those points today. I'm basically going to go back to where I started covering them in our notebooks and kind of go more in depth and try to answer some of the questions I saw. Um, but yeah, I'll also try to cover the other stuff, just not as deeply as I would, the more popular requests. So starting with kind of importing data and where do we get our data from? So people might have not seen this in the first day, might have not joined the first day. So we get to go to the Wolfram Data Repository, and this is the link to the Wolfram Data Repository over here. And this Wolfram Data Repository is a public resource, and it has a lot of data sets that we can use. So as you can see, we have a bunch of categories and a bunch of types of data as well. To use it, I can simply go ahead and search for whatever I want. So let's say I want to search for COVID. I can simply do that, and I get 10 items or 10 data sets that I can use. So these 10 data sets cover a wide variety of things, everything from epidemiological data to patient data to biochemical data and different stuff that we can all use to analyze the COVID-19 pandemic. So you can, if you open one of those pages for the data sets, you can read a lot about the data over here, and you can also have example visualizations, and you can also look at the source metadata down here. And if you want it in a notebook form, you can simply click this button, and it downloads into your computer as a notebook that you can manipulate very easily. So I can go ahead and kind of manipulate this however I want. So how do we get this into our notebook? So we get it to our notebook using the resource data function. But before I did that, I did a resource search for the keyword. This makes it easy to know what the names are for different types of stuff. So if I do a resource search for COVID-19, I get stuff, different types of resources that are related to COVID-19, and I can pick whatever one I want. And the most important thing before I get started is deleting the object corresponding to the data set. The way I can do that is calling the resource object for the data set and using the delete object function. After that, I can simply use the resource data function over here, and I import the data into my notebook. So as you can see, this is a very big and extensive data set. It covers a wide variety of things. And let's just get started with some basic data analysis. So basically, it's really important to remember that the order of kind of data extraction, so this will go row, comma, column. So here would be, if I call all comma 2, I would be calling all rows in the second column. If I only put in 1, I would be only calling the row number. So here, I would only be calling the row number 10. But if I, for example, a 2 in the beginning, I would say, hey, I want the second row of the 10th column. 10th column doesn't exist, so it's probably just going to error. But then yeah, that's one of the most important things to do. And if you want the entire column or entire row, entire rows, so you can all function over here. I can use the span function indicated by the double semicolons to indicate that I want a certain span. So the span works on rows, but once again, if I use the same syntax over here, I can use it for columns. So it's really important that it's row. It's row comma column. And the span basically goes from 2 to 10. So that's what my data returns. Instead of giving a number, so confirmed cases is the 4th column. Instead of giving a number or counting, maybe you have 100 columns and you don't want to count confirmed cases column is. You can simply call the column name. So you can simply say, hey, I want the 10th row of the column name confirmed cases. And once, if its capitalization is correct and everything's correct, I can simply get whatever's in that cell. So right here, I get whatever's in here, and it's a time series. So time series are basically specialized plots where the x-axis is dates, time intervals or dates or date objects. So I can visualize this very easily using the dateless plot function. I can simply, so I set a variable here equal to my time series, and I can visualize it using, the dateless plot function. I can also use a different plot theme, minimal. So here we can touch on a little bit of, plot themes and everything. So plot themes are really useful if you want a specific look. So we can go ahead to the documentation and see what types of plot themes are available. So, we can have, a monochrome plot theme, we can have a detail plot theme, and these are all applicable in different domains. So this might be this plot theme of detailed. Let me enlarge this really quickly. This might be applicable, in a more scientific setting. This might be given, in a paper where it's monochrome. And there's a wide variety of things that you can use. You can have, a scientific, have classic, have minimal, and I recommend you check out the plot themes and different options to really get at how visualization can help you and making the most alluring visualizations. So let me magnify this a bit because so yeah. I can also plot it on a log scale. So log scales really help us make sense of when a particular epidemic is leveling off. So here you can see that New York is leveling off, and once you get to kind of it going down, then you know that, hey, this is good news. I can apply the daily number of new cases using the differences function. So I'm simply applying the differences function over here, and I can use, once again, the dateless plot function to plot the moving average of the differences. So the reason I'm using differences over here is I want to get the daily case numbers, which I can't get over here because this is cumulative. So using the differences function basically gives me the differences between each day, which gives me the daily case numbers. Now, as you can see, the more I average it out, the more smooth it looks, and the more ready we can say, hey, this is the peak over here. We can also use a different function to smooth it out. It's the Gaussian filter, and I can simply apply it, and there's a kind of the N right here basically says how intense do I want my Gaussian filter to be. So yeah, let's continue on with entity properties. So properties, kind of the theory behind properties is you can use a specific entity, whether it's a country, it's a person, it's anything else, and you can use its properties to do data analysis and kind of have this vast array of computational knowledge that you can use to analyze data further. And you don't have to, for example, let's say you're analyzing COVID-19 data. And you have the COVID-19 data, you have the case numbers, but let's say you want to analyze it against something else, like county income, average income. Instead of having to go web scrape for data like that, or go to maybe the Bureau of Labor and Statistics, and kind of import it, clean it once again, and do this very lengthy process, you can import it directly into your notebook through a very simple call. So calling out, the 10th row's administrative division, we get this object right here, which is New York State. As you can see, entities can either be, this kind of object icon looking figure right here, or you can enter them through text, through the entity function. Either way, they act the same. The way that I like to enter them is using control equals. So once I use control equals, I can just type in wherever I want. So let's say I want New York, New York State, and I can simply press enter. So it tells me, hey, is this correct? So I can either say there's an alternate interpretation, so I can use it as a word, I can use it as a city, or I can just accept this interpretation, and it just tells me, hey, it's the administrative division of New York, because there's different, names. So you can have, for example, Atlanta, where Atlanta could be a name, it could be something else. So it's really important to check what the kind of entity type is before you move on to make sure that you're getting the right information. So I can call out its properties using, its properties property. And the way to call out property, so the kind of generic way is using entity and then kind of property name. So let's say this is my entity. I can simply put in brackets that I want, this property, and I put the property name. Oftentimes, so number of aggravated assaults is aggravated assault. So it's important to make sure, kind of hover over these to make sure what their actual names are. So as you can see, we have a lot of different things we can look at. So country, county sales tax rate, average earnings per job, employment, and so many other things that we can use to our advantage to do any type of data analysis. So this is especially true of kind of places in the U.S. So especially if you're doing any type of U.S. It's very likely that you can find whatever you want in these entities, and all of these are up to date and accurate. So there's no worry about that. So once again, I can use the same syntax I showed above to get the population, for example, of New York. So if I run this, so yeah, we get 19,746,227 people. And I can also just call out, so let's say I want a particular icon over here. So I can just maybe copy and paste it. So I'll take this, I'll copy it, and I'll just paste it here. And I get the subdivisions of New York. So I can either enter, it as a string, or I can enter it as another entity for the property. So now on to using entities, but really this section I'm really going to try to touch on kind of selecting data. So the most important, so this is the kind of format for selecting data. So let's say I have my data, so let's name it, just data. And so I'm going to have my data, and I'm going to have select first, and select, so hashtag column name, so column equals, let's say some entity or some object, right? So this time we're looking at entities. So let's say column is equal to entity, and make sure that we have the pure function, indicate that it's a pure function after. And this is basically how you select a certain thing from a data set. After that, you can do certain things with your data. So if I want, instead of just the entire row, I just want, for example, to do a certain operation with that row. So once again, I can use the syntax of hashtag column. So let's say the confirmed cases. So I can just say I want the confirmed cases divided by the recovered cases. So I can just do confirmed cases and then divided by recovered cases. And I can, once again, I have to put my pure function after that. And this is so I do this operation. So on the column name, which is equal to, the row name, which is equal to entity, I'll take my confirmed cases divided by my recovered cases, and that's my output. So it's really important to keep this in mind for, if you're doing any type of data extraction. So essentially that's what we're going to do. So this is our data right here, and we're selecting the first instance of the administrative division equal to New York. So what the computer is going to end up doing, so if you go up here, is it's going to look through this column right here, and it's just going to select the first time it sees New York, which is right over here. And once it sees this, it's going to spew out this whole entire row. So it's going to spew out this entire row corresponding to New York, unless you tell it, hey, I want to do a specific operation with it. So this time we're going to say, I want the death rate per, or cases per 10,000 inhabitants. So the way to do that is, use confirmed cases and divide that by the administrative division's population. So again, I'm using the entity's properties and specifically entity population in my calculations, and just multiplying that by 10,000 to get the cases per 10,000 inhabitants. I end up getting this time series, and I can plot it using the dateless plot function. I can once again, use a different column. So instead of finding cases per 10,000 inhabitants, I can just simply replace, this with deaths, and I can get deaths per 10,000 inhabitants. And they look very similar, as you can see. They evolve very similar. So there's about, 15 or 16, 17 deaths per 10,000 inhabitants in New York. So exploring elements of the data set, we kind of touched on that before. Really, in any generically, so let's say you have, resource data. So I'm giving these kind of generic codes only to kind of further show, syntax and everything like that. So let's say my resource data is name, name of the data set, comma, element name. Kind of the generic way to enter an element. And so here we have, my data set's name is epidemic data for novel coronavirus COVID-19, and my element name is for Brazil provinces. So that's how I enter it. And it's important to remember that elements of data sets are either there to organize certain data or apply certain functions to certain data, whether it's a histogram, a tally, a bar chart, a plot, whatever it may be. It kind of helps you skip that middle step of you doing it yourself. So this is Brazil element, and once again we called it using the same code. I want to do some basic data analysis on kind of the elements themselves, and I'm going to try to use this as an opportunity to further show kind of how data extraction and analysis works. So I imported the world countries element right here, and let's try to say I want visualizing COVID-19 deaths per 10,000 people across the EU. So this is a really important point to touch. It's kind of the presence of entity lists and stuff like that. So once again, we're using select, and select basically says I'm selecting. If we go to this documentation over here, select. So let's say we have a list. It picks out all the elements of the list for which that criteria that we put is true. So it's about trues and falses. So member queue is exactly what we want. Let's say we want to get a specific criteria where we say, oh, it has to be a member of this list. So we set up our list, which is the entity list for the European Union. And if we, we can run this on our own to see what it looks like. So yeah, it just gives us the entity list of all the entities in the European Union. And the way we can enter it is simply, using control equals and typing whatever we want. Let's say European Union countries, and we're going to get that. So back to our code. So basically select functions off of trues and falses. So we want all the European Union countries to be true and all the non-European countries to be false. So we're going to use the member queue function and use the entity list for the European Union. And the member queue function's syntax is list first, and then what you want it to look at. So we want it to look at the country column, and select is going to be here, and then my pure function is going to be here. So we got that, right off. But then after that, we're going to do some of our own kind of manipulation. So it's going to be this right here. We're going to map each country to 10,000 times by the last number of deaths divided by the country's population. And that way we get, COVID-19 deaths per 10,000 people for each country associated with the country's entity. The reason I like entities so much is, you have these properties where you have, kind of population, and it can also be really for other Wolfram language functions like what I'm about to see here. So value plot function to plot all these entities. And if I only had, Austria in a string form, it wouldn't be plottable using GeoRegion value plot. It needs an entity, which gives it information about, where it is to, actually be able to plot it. So GeoRegion value plot function, it's really important to know that there's a lot of ways they can visualize geographic data. The main ways we touched on today, or in the past 4 days, were GeoRegion value plot and geohistogram. So geohistogram is all about kind of big data sets. So let's say we have 27 here. We have 27 elements, but let's say you want to visualize, 1,000 different things. A list of 1,000 different entities, or a list of 1,000 different geopositions. So I personally prefer geohistogram when there's a lot of data, and also when the data is given in geopositions instead of regions or icons, because geohistogram can actually work with geopositions, a very precise geoposition and given in latitude and longitude, while GeoRegion value plot cannot. So that's kind of the most important difference between them. So I can also try to kind of visualize COVID-19 deaths for 10,000 people across Asia. Once again, very similar code, but this time I'm going to be dealing with differently. So instead of saying, hey, I want the entity list of the European Union, I'm going to look at Asia, the geographic region, and I'm going to take the country's property of it. So that gives me the list of all countries in Asia. And basically, I'm going to use the member queue and select functions once again and apply the same transformation, country associated with 10,000 times by the last value of the number of deaths divided by the country's population, to get something that looks like this. And I can plot it using the GeoRegion value plot function. Okay, am I not muted now?
Yep, you're good.
Okay, so hey everyone. We were just talking about kind of how to import data into our notebook and how to do some kind of basic data extraction using, kind of column, row name, and also using the select function. So we're going to be, for those just joining, I'll touch on that, a little bit later on, just to, recap that for you all. But then let me just continue where I kind of left off. So where we left off was we visualized kind of the Asia death rate per 10,000 people. And the way to do that is, let's just go ahead and kind of enter the syntax. So let's say I have some data with my variable data. So that is my data, and I want to select a specific set of rows. So let's say I want to select, a set of rows from a certain list that I like. So let's say I'm going to use the select function, and then I'm going to use the member queue function, and then I'm going to use whatever list, and then whatever column I want to look at. After that, I can simply use the pure function here to indicate that it's a pure function, and kind of use this right here, and then do whatever calculation I want. So let's say I want, country to the deaths column, and that's essentially going to give me my countries associated with my death column. So let's kind of analyze this code further. So we use the select function. Select function is a kind of a binary function. It works off of true falses. And if it's a true, it's going to take that row. It's going to put it in your new improved list. If it's false, it's going to ignore it. And I'm going to use the member queue function over here to say, hey, I'm going to be looking at if it's in this list. If I'm looking at the country here. If the country name is in my list right here, then it's a true. If it's not in my list right here, then it's a false. So anything with a Q at the end, it's going to be, is this, so member Q, is this a member? Even Q, is this even? Odd Q would be, is this odd? So these Q functions are very important for any type of data analysis. And we're going to be using the member Q one right here to determine whether a certain row is a member of a certain list that we would like. And it's really important to remember that these are pure functions. So we're going to add the and symbol or the ampersand over here. So once we get this, get this calculation off, so we basically are associating each country with 10,000 times by the last value of their number of deaths divided by the country's population. I can use the georegion value plot to plot it. Once again, I'm using the georegion value plot here because we don't have, hundreds of rows of data and we're using entities. So georegion value plot is better suited for this than geohistogram or any other geovisualization plot. I can customize the plot's colors. So using the color function, I can call out a specific color way using color data. So we can go ahead to the documentation of color data and kind of look at the scope. So schemes and collections. So there's there's sunset colors. There's a color list over here, midnight blue. So there's a lot of different things that you can kind of explore using color data. There's a lot of different colorways that you can explore. So this time I just chose a simple alpine colorway, and this is what I ended up getting. So I think this is, if you're kind of presenting it using a certain theme, let's say you're making a presentation on, COVID-19 in Asia, and your theme is kind of blue and green, this would be better suited than, something like this. So this is kind of the theory behind visualizations. A lot of times it wouldn't matter, what color you're using, but aesthetically pleasing visualizations are also a thing that, you kind of have to keep an eye out for. So that's why there's so many options in the Wolfram language for, kind of customizing your plot while still keeping it, the same accurate one that you intend. I can add customized geolabels. So geolabel, I can simply say geolabels option, set it to true. And label style is an extra thing that, you can customize what the geolabels look like. So I can, put the font name here. I can put what type of, font size I want to use and different stuff like that. So I had a question. So didn't you say the other day in some cases you must apply entity lists before doing selections? When is that necessary? So I had two examples. So before maybe everyone came in. So two examples. So I can either use, so Asia, if you notice, so this is a geographic region. And I'm using the country's property of this geographic region to get this list right here. I can use another type of code. So for example here, I simply use entity list of the European Union. So this isn't a geographic region, it's a set of countries. So if we look at it, it's not even an entity, it's an entity class, and that's denoted by the kind of the kind of square right here. It tells you that this isn't really an entity, this is an entity class. An entity class is basically a type of entity. So this would be either, very broad thing like, people or, countries or something like that, or, just European Union countries. And the way to enter that is, as you can see, entity class, brackets, country, comma, European Union. And that gives you, European Union countries. An entity list is used to get the entities in that kind of entity class. I could also just use, the geographic region. So I want to look at Asia, the geographic region, and I'm going to apply the country's property to that. And I'm going to end up with the same output in the fact that all of it is, both here and above. I'm ending up with a list of entity countries. And both of them I can use in combination with the select and member queue functions to select specific COVID-19 data. So moving on, we're touching on the Indian provinces. Once again, so this is rather simple. We're looking at all rows, and then we're applying this calculation right here. We're doing administrative division, map to confirmed cases, the last value of the confirmed cases. Once again, we have to remember that this is a function, and we're applying the georegion value plot function. So there's various ways to apply functions. So many of you may be already aware, but I can either kind of apply a function like this, where my input is right here, input. I can do input and then kind of apply the function after, like this, or I can do georegion. So let's do georegion, can't type, at input. So that does, all of these codes are equivalent. It just depends on, kind of styling, and sometimes it's helpful to have, this to make your code maybe clearer or more easy to understand. Anyways, so we're using the georegion value plot function and getting this visualization right here. I can enlarge it a bit. So this is the visualization. I can also look at, a heat map in terms of confirmed cases per square mile. So this time I'm going to be using much of the same code, but I'm going to be trying to use the entity property area of my administrative division. And to make sure I only get the number instead of, like square miles or something like that where I have a unit, I'm going to use the quantity magnitude function. But I end up with this very bad looking visualization. This isn't very insightful. So it's really important to keep in mind that when we do make visualizations, we want them to be insightful. We want them to tell a story. We want them to pack as much meaning as possible. And this is packing very little meaning. As you can see, I can't really tell how kind of between each administrative division in India, how the confirmed cases per square mile is varying. Delhi right here looks like it has very dense in terms of confirmed cases, but then other administrative divisions, I can't really tell how they compare. So the way to kind of make it more meaningful is using a plot range. So here I'm telling the computer, hey, I want you to make the scale from 1 to 10. So that's what it ends up doing. So I can, oops. So right here. And I end up with a much better looking visualization than I did before. So I can actually compare, hey, like Uttar Pradesh is, different than, I don't know, like Manipur in India. So we can kind of compare different regions and different states in India using a better visualization that we weren't able to using this bad visualization. I can alter the image size to obtain a clear plot using, image size and set it to large. Russian provinces, much of the same kind of content, same type of code. So US states. So we're going to touch on a specific thing in the US states, which is linear fitting. And I'm also going to touch on another form of setting up my data. So before, if you noticed, when I set up my lists over here, where is it? Over here. So I'm simply mapping an entity to a number. But then here I basically want to map my entities, or I want to get a list or a kind of a data point mapped to an entity. The way the reason I want to do that is I want to eventually plot this on a plot and plot all these points and kind of visualize where each state lies. So I can use very similar code. So instead of just using without a list, I'm just going to put a list right here. So I'm going to use all rows, and I'm going to put my list right here. So I'm going to say in the first element of the list, I want the insured population fraction of my administrative division. The question I'm trying to answer is there a correlation between health insurance coverage and COVID-19 deaths? So in the first element of my list, I want the insured population fraction of each administrative division. In the second, I want death rate per 10,000 people, and we've already talked about this before. And eventually, I want to map it to my administrative division. So I end up with this list right here that I can plot using the list plot function. So I'm going to plot this using the list plot function. There's a lot of options over here, but all we care about is this is list plot and my variable above, which corresponds to here. And also, I'm using a labeling function equal to tooltip or like set to tooltip. So when I hover over something, so let's enlarge this a little bit. When I hover over something, I can look at this is Connecticut, this is Massachusetts, this is New York, and elsewise. So let's try to use linear fitting to try to extract, whether there's an actual correlation or not. So as you can see, if I take, so this is above is a list of associations. So if I take the keys, so keys would be right here. Keys would be on the left, values would be on the right. So the key is basically, that your key to the value. That's how I think of it, is your key to access the value. We could have done this differently. We could have done, kind of the opposite. But the reason I'm doing this is if I did the opposite, I wouldn't be able to hover over things and select them. So I would be basically plotting, it would be more complex to get this plot right here. So, and normal just gives it a normal form. So normal form is basically, instead of a data set, it's going to give you, an association or a list of associations, something like that. So the way to kind of set up my, specify. So the way I specified the continental state, so I'm answering this question, is using elements. So this is my US states element. So I didn't need to specify anything because this was already set up for me using, kind of the elements of the data set. I can also, use US counties. I can use world countries. I can use, Brazil provinces. There's a lot of different elements that you can explore. So back to setting up our model. So the way we can set up a linear model is use the linear model fit function. And the generic way to use this function is, so I have my linear model fit function, and then I have my data, and then I have my variable, which is x comma x. So that basically tells you that I want a variable in x. So basically, I did some data cleaning over here because there was a missing element in my data, but then this is kind of just very simple data cleaning. And the most important thing, if you're working with clean data, that is, you can just put your data in here and then put the variable that you want your model to be in. It's x. So there's a lot of different properties of models. So this applies to both linear models, the one we just did, and non-linear models. So whether it's like an exponential model, a logarithmic model, any type of model, they have different types of properties, and they're listed right here. So you enter them just like you enter entity properties. You put the name of the property in brackets and as a string, and you get it back. So I'm calling out the R squared property of my model, and I get a very low R squared coefficient. So it tells me the correlation is shaky at best. And I can plot it. It's important to remember that if I want to plot a linear model or any type of model, I have to call the model name, and I have to say that this is a function of x. And then I have to, the normal syntax of a plot function is basically, x from 70 to 100. And I can use plot style and other options to specify what type of plot I want. So yeah, and I'm using the show function here to show multiple plots at the same time. So show basically uses, I can show 10 plots at the same time. So we have a question from Alejandro. How can I know what else than just US states? So if I scroll up, when I first touched on entities, or when I first touched on elements, I can say I want, I can call my resource object, and in brackets, I want its content elements. So I have all these elements right here, and you can do this for any type of data. So generically, you call the resource object corresponding to your data set, and you put under brackets that you want the content elements of your data set. So I can do more analysis. So this is kind of another property that I'm analyzing, median age. That can be analyzed too. So very similar code. Only thing that I replace here is instead of looking at people with healthcare, I'm looking at median age. Similar plot once again. I could hover over Connecticut over here. I think that's Maine, New Hampshire, Vermont, West Virginia, and so on. This time I can use a module to kind of compress the code needed to plot both the best fit line and the data. So modules function on basically kind of local variables, and I'll touch on how they differ from blocks later on. That was a common question that was people were confused about. But essentially, module, which we're going to be covering here, you set up your variables. So here I have two variables, list and fit. And if I want, so I can either just set up, so list, I could have defined fit inside my list right here. But then fit right here needs list. So what I'm gonna do is I'm gonna set up this, so it's gonna be some generic code. So let's say I'm gonna say my first variable A equals something. And then I'm gonna say, hey, I also have another variable, and that variable's name is B. And after that, I'm gonna say, oh, B, by the way, B is equal to A squared. And then after that, I'm gonna put a semicolon to start, the kind of code that I want. And then I can do whatever I want with my variables B and A. So that's kind of the generic code for entering kind of modules. And modules, the reason for them is to kind of speed up computation most of the time. There can be, used in other purposes, because local versus global variables, that kind of gets complicated. But then essentially local variables, which are basically variables that, are stored in a single computation, are speed up the computation process. So instead of having to compute fit 10 times or list 10 times, you're only having to compute it in the beginning. So this is essentially what we get. And as you can see, it's a very shaky, has a R-squared coefficient of 0.007. So it's a very shaky fit at best. But then we do know that, COVID-19 does get more severe with age. So this might be just a telltale sign that there's many other properties that kind of go into that death rate for each state. So I can look at US counties as well. This time I'm going to be taking the data for the largest 20 counties in terms of confirmed cases. The way I can do that is use the take largest by function. And essentially I'm just going to call out the county, confirmed cases, and deaths. So this syntax right here basically gives me a way to, instead of kind of importing the entire data set, I can only, in my new data, I can only say that, hey, I want just these two columns or just these three columns. So I end up with this. So it looks like LA County is the highest, followed by New York City, and then Miami-Dade County. So I'm setting up my data. The question I would have liked to answer was, is there a correlation between per capita income and death rate per 10,000 people? So once again, I can use kind of this abstract thing where I'm like, this is the first element. So my first element I want is the county's per capita income. My second element, I want it to be the last value, the number of deaths divided by the county's population. I can map all of that to the county. So this is essentially what I get. And I can apply the data using very similar code to what I did above. So this is the South County, this is Suffolk County, Orange County, Palm Beach County. So there's a lot of different trends here that we can say that maybe there's a slight trend. The way we can kind of make sure is using a linear fit. So once I run this, it looks like there's a slight negative correlation, very slight. As you can see, the R-squared coefficient is very, very low. I can also look at different counties. So I can look at the top 50 counties, and the way to do that is simply, instead of take largest by of 20, I can take largest by of 50, and I can do the same for 200. And it looks like there's a very slight correlation between per capita income and COVID-19 death rate, which kind of makes not a lot of sense, but maybe that's due to maybe older people have a higher average income. So COVID death rates would be higher in counties where there's more old people, and that's medically verifiable. So let's move on to mathematical modeling. So that was another thing that people were confused about. How do you build mathematical models, the SIR model? So let's touch on kind of the idea of compartmental models again. So basically, compartmental models function off the premise that we have these 3 abstract compartments or 5 abstract compartments, whatever number, and people move in from one compartment to the other. So essentially, they're looking at, it's like a kind of population science. Why when people are looking at different populations and how these different populations contribute to the spread of a particular disease. So we know that epidemics happen because of diseases that can be spread between person to person very easily. So stuff like the flu, coronavirus, Ebola, so those are epidemics. So that's what the model tries to describe. So it's infectious diseases. And essentially the most basic of these models is the SIR model. So it tries to kind of model the epidemic in terms of people who are susceptible. So, the first compartment right here. So these people are people who have not contracted the disease, but they are susceptible to it. So they can contract the disease at any time. People who are infectious or infected. So these are people who have contracted the disease and can infect anyone at any time. And people who are recovered. So these are people who have already gotten the disease, and the premise is these people already have immunity, so they can't really get it anymore. So as you can see, there's more complicated ways of looking at this. Recently, there's been research saying that people can actually contract COVID-19 again. So you could see how that makes the model much more complicated. But we're going to function off the premise that, hey, recovered people are not going to contract the disease, at least in the foreseeable future. How the model operates is through a list of differential equations. So essentially, it says that between these compartments, people are moving around all the time. And since differential equations, basically all they try to do is model change, it's a very good way to express the language of epidemic evolution. So there's certain rates that people convert from susceptible to infectious and from infectious to recovered. We're going to be naming them B and K, and we could set these parameters into our differential equations, and we can try to fit them based on the data we have. And through optimization and through the various algorithms that Mathematica has for optimization, we can build very accurate models for kind of any type of epidemic. So today we're going to be looking at a very simple flu epidemic in a boarding school, and also COVID-19 pandemic in South Korea. So I mean, the herd immunity model, that's another that it's not really supposed to model, kind of the epidemic's evolution. It's more about, it's more of an approach to solving, kind of an epidemic solution. So it kind of, the herd immunity model, if we were to try to apply it to the SIR model, would say, hey, people are going to become, B would be really fast. So B, the probability of infection would be really high. So that way people can go from susceptible to infectious in a very fast period of time. And then they can go to recovered also in a fast period of time. And once they get to recovered, they can't go back to being infectious or infected. So that's kind of how it is applied to this model right here. So there's different approaches of, kind of public health approaches to this, and I'm not going to discuss that right now, but I am going to discuss what the models are that epidemiologists and public health experts use to make those kind of approaches for public health. So first of all, I'm going to set up the equations. So I touched on these equations a little bit yesterday, but essentially they kind of they're very simple and they're all about the size of different compartments. So my parameters, so I first want to look at, how, this epidemic evolution looks like. How does a SIR model look like? So basically what I'm gonna do is I'm gonna enter some initial values. And these initial values are just gonna, serve as, random values. It's just gonna serve as a way to visualize what the model looks like. So I'm gonna say that B, the probability of infection is 50% or 0.5. And K, the amount of time to recover, is going to be 14 days. We enter it as the reciprocal, so it's 1/14. I can get a solution using ND-solve. And the way to kind of enter it in ND-solve, so I have this kind of the generic syntax, ND-solve, and I'm going to put my equations right here, and then my initial conditions right here. And I'm going to close my list, and then I'm going to put the variable names. So variables over here, start a new list, and basically my time period. So time and variable, time plus variable that you want to solve for. So this is essentially the skeleton of any type of ND solve function to be used in mathematical modeling. There's different ways that you can input ND solve function, as you can see here. But what we're trying to do is kind of model epidemics, and that's going to be the most generic. The way I showed you is going to be the most generic way to enter it. The documentation is your best friend. So each function has a lot of different applications that you can kind of scroll through over here to get an idea. But we're going to be using it for a very narrow purpose here, and it's modeling epidemics. I can generate an individual graph. So what I get is a bunch of interpolating functions. I can generate an individual graph for each variable by using the replace all function. So S replace all solution is going to look for, hey, where is the S key? And it's going to look, oh, here's the S key. So I'm just going to give you this output right here. So that's essentially what it ended up giving me. And I can plot it using the plot function. This is what it looks like. So very consistent what we know of epidemics. So it has a nice looking curve. And most epidemics, not 100% of people are going to be infected, but it's still really wonderful to see that, hey, these models actually do very well in modeling specific epidemics. So now we can touch on a little bit of the block function. So let me show you kind of an example of why block works here and module doesn't. So let's say I use module. So it's almost the same syntax for block and module, but if I use module, it's gonna give me a lot of errors. And the reason it's giving me a lot of errors is because I used B and K before. Block and module both talk about local variables, but block is better suited for variables that are used elsewhere in the data set, in the notebook. So if I used B before, and I'm gonna use B again, I'm better off using a block function to try to manipulate it locally, instead of manipulating it using a manipulate function globally. So what I'm going to end up doing is have this manipulate function right here. I can manipulate it however I want to visualize how different parameters and varying them contributes to the evolution of a particular epidemic. So good question from Yanis. For SARS-CoV-2, should we also create? So yeah, I touched on that a little bit. And in actual models that public health experts use, there's going to be some element of that. But it's actually really surprising that for at least for a few months, it looks like you do have some type of immunity, and that way we can actually model the epidemic very well, even with a simple model like the SIR model that doesn't account for everything that kind of happens in terms of people getting reinfected. There's a lot, we're also forgetting a lot of different compartments here. So people can be quarantined, people can die from the disease, people can be there's an incubation period where people were infected, but it hasn't manifested in themselves yet. So there's a lot of different things that you can add. And the actual most accurate models are going to have dozens of different compartments that go all over the place. But for the sake of this introductory course, I'm only going to cover the SIR simple model. So yeah, we can enlarge this just so you can get an idea. So Y corresponds to K, which is the time to recover. So since it's the kind of it's the reciprocal, increasing it would basically mean that you're increasing the time to recovery. So you're decreasing the time to recovery, so it's basically going to flatten out. Decreasing it would make it very, very much a high, sharp peak. Same with X is the opposite. Decreasing it would give you, a less sharp peak, and increasing would give you a sharp peak. So let's apply the model to real data. So I have this textbook influenza data set. I got it from Robert Nachbar's community post on the subject, and has a different, it's very small, but I'm going to try to make the best out of it. So first, pre-processing. So these are data objects, and we don't like data objects when we're dealing with math, where we try to convert everything into numbers instead of entities or objects, because that's the language of math, that's the language of differential equations, is through numbers. So I'm going to try to convert these dates into days since the epidemic started. The way to do that is I'm going to set up my first date, my last date, and I'm going to use the date differences function. And that gives me how many days is between the first date and the date that I'm looking at right now. And I get this refined list right here. As you can see, it's very small, but we're going to see if our model does a good job of modeling it. And I can also get the influenza data number of boys, and that gives me my population size. So I don't have to do any guessing in terms of population. You can visualize the data over here. Let's expand this. As you can see, it's a kind of a rough looking curve, but let's see if my model can try to approximate that curve. So now I'm going to set up the data fitting. So I'm going to start with the clear all function to clear all parameters b and k. That is to kind of refresh those parameters and say, hey, I want to look at basically fit those parameters instead of set them before, because we're trying to find the parameters which actually fit our model. And we're going to be using the parametric ND-solve function here. The reason we're doing this is because, and not using the ND-solve function, is because we actually have parameters here that we have to solve for. And we're not going to be solving for them right away. I'm going to be creating a dynamic module first to try to manually fit the data, as you can see here. So I can basically manipulate it until I think I have a good guess of how the red, which is the infected compartment, matches with my data in red, which is also the infected data. So the syntax over here is rather simple too. So I have my parametric ND solve. So parametric, let's kind of give a generic form of this syntax. So I have my equations, and I have my kind of so join function over here. The reason I'm using it is to join different lists. But essentially, if I were to enter this manually, is I would use equations, options, right? And then I'm going to use my variables, and I'm going to put them inside a list. So variables here, variables that I want to solve for, time, interval, or whatever you're solving for, whether it's any type of variable, whatever interval, and then my parameters. So it's really important to remember that this is the syntax for entering any type of parametric ND-solve function. And parametric ND-solve can work with non-parametric functions. The only big difference that is very important is parametric ND-solve returns a parametric function, while ND-solve alone returns an interpolating function. And since we want to vary the solutions to this using different parameters, it's way better off using parametric ND-solve because we want a parametric function. Dynamic module is very similar to module. It's only dynamic, so it's it's more it's meant for stuff like manipulate and stuff like that. So I'm basically setting up my local variables, my local population, local data, susceptible, infected, and so on. And most of the code is just kind of options. So you don't really need to do this step, but it's really important, in my opinion, to visualize that you're on the right track. So let's go to fitting the model. So this time I'm going to be using nonlinear model fit instead of a linear model. As you can see, this isn't a place where linear models would be efficient or accurate. So the way to enter it generically is, I have my nonlinear model fit function. I have my data. I have kind of the function I want to model and its kind of parameters over here. And then I have my guesses. So let's say guess 1, guess 2, and so on. And I also have at the end my variable t. So this is essentially the form. So the reason I need a parametric solution is because I'm varying it by parameter. So if I don't have a parametric solution, let's say I only have an interpolating function, it's going to be really complex because I'm basically going to have to set up a manipulate outside of an ND-solve to locally vary the variables b and k. And that's going to be a really complicated task computationally, and it won't fit well with my nonlinear model fit function because you can't fit nonlinear model fit function necessarily needs a parametric function if you want to, kind of solve for parameters. So while it might work here using some, computational heavy code, it's not going to work with my nonlinear model fit function. So back to kind of our discussion. So I'm basically assuming that the initial infected population, so as you can see, we kind of gave the order of the variables here. So N is the initial is the population, I0 is the infected population, B is the time, is the probability of infection, and K is the time for recovery. So I'm going to assume that, initially we have one person that's infected, the population size is given, and then B and K is what I really want to solve for. And that's what I kind of try to guess for in my manipulate over here. So I end up with this fitted model, and I can explore properties of the model like I did with the linear models before. So here's the R-squared coefficient. It looks like it's very good. I have my fit residuals, which are basically, the actual number subtracted from the model number, the difference between them. And I have a lot of different properties that I can also look at over here. I have my fit properties. And I can plot the fit and visualize the fit versus the data using the show function. And as you can see, it's a very good fit. So I only have 10 more minutes, I think, or 15 more minutes remaining. So I'm basically just gonna touch on a little bit of some data extraction because the rest is basically just another model applied. So I'm gonna touch a little bit on this, and I'm gonna touch a little bit on kind of comparing the models. So once again, deleting the object, and now I'm gonna set up my variables. So infected, recovered, deceased, and that equals, I'm gonna use, my select. So this is the data, and I'm gonna select the first instance of the country, South Korea. And what I'm gonna end up doing is I'm gonna use some operations on my columns. So I'm gonna take the confirmed cases, and I'm gonna subtract them from the recovered cases and the deaths. This is to get the infected active population, and then simply recovered cases and deaths already set up for me. So I get these time series right here, which I can plot using the dateless plot function. I also have the map index function over here. So it's important to remember, and when you're using map index is a way to kind of visualize or index a certain list. So #1, or number 1 would be your actual list. So let's say my list is 1, 2, so 1, 2, 3, right? #1 would look at 1, 2, 3. #2 would give you so #2, if you were just to apply it, it would just give you one, or just give you an index like this that you can add to each of your lists right here. So what I'm gonna do is I'm gonna take that number 2, which is gonna be the index, and I'm gonna take the first element. The first element rids it of that list, so I'm gonna end up with just 1. And then I'm gonna put comma #1, which is gonna give me my corresponding list element. And what I'm gonna end up with, since I have a list right here, so let's say it's 1, 0, and then comma 2, 0, comma 3, 0. And this is really important function for any type of indexing, whether you're looking at epidemiological data or, any type of data that concerns dates and times. It's really important to, use this function. So this is the SIR model, and we can try to apply it to COVID-19 data using a very similar method to what we did with the flu. So I'm going to set up my differential equations. Only difference here is I actually have an n because I'm not sure what my population number is. I can solve for the parametric functions, and I can once again use my manipulate and plot function to manipulate this manually. So I can manipulate different variables and different parameters to try to get an initial guess. Once I do, I'm gonna go ahead and use nonlinear model fit function. But before that, I'm gonna use basically what's called a statistical indicator, and use the prepend function to say, hey, we have different batches of data that I'm gonna fit to different models. So right now, I'm fitting to both infected and recovered. And since I have compartments for both and I have models for both, I also have data for both, I can do that very easily. I just need to tell the computer which is which. So I'm going to prepend or add a 1 to the beginning of the infected data. And as you can see, this is the infected data with a 1 in the beginning. It's a statistical indicator. And I'm going to prepend recovered data with a 2. And this is the recovered data with a 2 in the beginning. And I'm also going to define a fitting function for my models, and I'm going to set up different tags for different functions. So if the tag is equal to 1, then I'm going to set up I'm going to give it my infected model. If the tag is equal to 2, then I'm going to give it my recovered model. And these are all functions of T. So when I end up using the nonlinear model fit function, I can use my data like I would normally, my general data over here with the prepended numbers, the statistical indicators, and I can use my model which has the tags, and it's a function of both tag and T. And then I can enter my my parametric function, my parametric variable guesses, and I'm going to tell it, hey, this is a function of both tag and T. So I get this fitted model right here, and I can look at the fit residuals. And what does the fit look like visually? I can look at the parameter table first to make sure that this is a good fit. And once I see that the p-values are very low, I know that this is a good fit. I can actually compare the model with the fitted data using the plot function and combine it with the epilogue. So epilogue, as I touched on yesterday, is a way to overlay additional data or additional graphics on top of a plot. And as you can see, it's very similar looking model to the data. So I can apply another model. So this is a slightly more complicated model. It's the SEIRD model. And this setup is very similar. So I'm just gonna go through it really fast so we can finish in time. So start off with the equations. And as you can see, these are the equations in column form, and use the parametric and the solve function to solve for the variables and parametric functions. Use the manipulate to get an initial guess. This was quite a headache because I had to manipulate so many different parameters to get a good guess. And then prepend the data. This time I have to prepend 3 different data batches: infected data, recovered data, and deceased data. And the same thing for defining a fitting function. I have to use different tags, 3 different tags for 3 different models. And the rest is very similar syntax-wise. So I'm using a nonlinear model fit function and plugging in my data, my model, my guesses, and my variables. So what about comparing models? So this is going to be our last kind of point. So the way to compare models, there's different ways. I think the better one is using the AIC coefficient. So that kind of tells you a little bit more about model fit. So AIC, the lower the coefficient, the better the fit. And as you can see, fit SIR actually has a lower AIC coefficient. So it's really surprising to me that something like that would happen, where a more complex model would be less accurate. So what's going on here? What was wrong? I can try to look at the parameter table to make sense of it. So the p-value looks like in beta and zeta that it's very high. And when that happens, it either means that these variables are not important and we need to get rid of them, or that only one or the other is important and they're kind of correlated very strongly. The way to tell is using a correlation matrix. And as you can see, so it's variable number 2 and variable number 4. So we check 2, 4 and 4, 2. And it looks like these are very high. And if we look at the list for the number, looks like it's negative 0.99. And that means it's a very strong correlation between these variables. So it looks like the model couldn't really distinguish between these variables or these parameters. And therefore, it's way better if we were to just use 1. So the model can make better sense of it. In the end, we can just also look at it, the fit visually, and it looks like the deceased the deceased line matches very well with the data. as well as the infected line, but then the recovered model doesn't really fit. So thank you everyone for tuning into this course. So this is going to be the end of the course today. I hope you guys have a good time with the quiz. I tried to make it all code-based and try to only include stuff that I kind of included in my notebooks several times and touched on several times. So I hope you guys do a good job there. Thank you for listening to this course, and I hope you come to more Wolfram U courses later on.